Warahmatullahi wabarakatuh. In this video I'm just going to try and explain how to derive an equation for the mass flow rate through a pipe measured using a Pitot tube, and explaining about a velocity profile as well. So you have to start with the Bernoulli equation, which, as you know, is this over here. In this case that we're doing, the system is considered to be horizontal. Therefore, this part and this part, which are the hydrostatic pressures, they can be neglected because Z1 and Z2 are the same. So if you rewrite that equation, you can rewrite it without these hydrostatic terms. Then, when you come down to here, you will know that a Pitot tube has a stagnation point right in front of the entrance, right in front of the orifice, where the velocity of the air is zero because of the build-up of the pressure inside the Pitot tube, causing the velocity here to be zero. And so because of that, you can actually completely neglect this part, V2, of the Bernoulli equation as well, because V2 is zero, therefore all of that is zero. So you can just consider this part. P2 is known as the stagnation pressure, which is basically P1, the pressure at a point away from the Pitot tube, and the kinetic energy per volume of the velocity of the air at that same point 1. Then if you rearrange this, you can get an equation for V1, the velocity. You can get that equation as this. And we know that mass flow rate is this formula over here. So that's why we need V. However, it's not as simple as using this formula, plugging in V into here, as we did in the Venturi, because a Pitot tube is fundamentally different. A Pitot tube only measures the velocity at the point where the Pitot tube at the point of the pipe where the Pitot tube is placed. However, we know that because of the flow inside of the pipe, because of the no-slip conditions, and because the flow is turbulent, we know that the velocity is not the same everywhere along the pipe traverse. We know that in the center of the pipe the velocity is the highest, whereas the velocity decreases as you go nearer to the edge, reducing to zero velocity, the particles that are in contact with the wall. So it really depends on where you place the Pitot tube. Up here you would record a very low velocity. Over here you'd record the highest velocity in the middle, and over here you'd record the same velocity as that one, but it would be a very low velocity. This change in the velocity along here means also a change in the flow rate. The flow rate, the amount of air flowing through the middle, is much higher than the amount of air flowing near the edge every second. Every second more air flows through the middle than there. So that means the mass flow rate, it changes. The mass flow rate, it changes. It changes according to this relationship. If you draw a graph of this, you'll see that the mass flow rate is the highest at the radius, at zero radius, right in the center. And as you go further out towards the edges of the pipe, then the mass flow rate will reduce all the way down to zero, either way you go, and it's symmetrical. Therefore, this graph is basically showing the relationship between the mass flow rate and the radius at which you're placing your Pitot tube. And this can be expressed as this equation here, which is basically the same as that, but it's saying that the change in mass flow rate from one point to another is the same as rho, which is from there, change in A, because you're looking at a change in the mass flow rate, therefore you're going to look at the change in area. So if you've come from there to there, for example, then you're going to look at the change in that area, and you'll find out the change in the mass flow rate. So that's what that dA is. And VR just means velocity at that radius where you've measured using the pitot tube from. So VR if I've measured here will be different from VR if I've measured there, and it will vary along the pipe. This dA we can actually put something in. We can rewrite this as that. We can say dA is basically 2 pi r dr. Why it's that is, if you look at this diagram here, if you consider that width of this section that we've just cut out from the pipe, that cylindrical element, the width of it is dr. It's basically, that width is so thin that you can consider it as a really long rectangle, just joint together in a circle. So a rectangle, you can just do height times width. So the height in this case of the rectangle, if you stretch this out as a rectangle, the height is dr, and you're timesing it by the length, and the length is the circumference of this cylindrical element, 2 pi r. So 2 pi r dr, that's what your change in area is. So the change in area from there to there, that's basically this area here. Put that into that equation here, and this is showing that relationship. This is basically this graph in an equation. Now the area underneath this graph is the total mass flow rate. This is the relationship between mass flow rate and the radius, and the area under it is the total mass flow rate. So you know from A-level maths that if you want to calculate the area underneath this graph, you can integrate this equation. And when you integrate this equation, you've got dm. If you integrate that, you'll get m, which is what you want. This is the mass flow rate, which is what we want. So we could integrate this. It would be great if we could integrate that. Then we would end up integrate this side as well, and we'd end up with an equation for the mass flow rate, job done. But we can't do that. We can't integrate this because we don't have a curve. We don't have a curve, a perfect, complete curve for every single velocity at every single point. What we have instead, we just have readings. We have discrete readings for velocity, because we're gonna move the pitot tube in the experiment to different positions and take readings at those points. So we've actually just got discrete values. We've basically got a bunch of trapeziums. If you draw the graph from point to point, we've basically got trapeziums. But you know from A-level maths that you can actually find the area under this using the trapezium rule. And the trapezium rule is basically, if you remember, it's just like a sum. It's a sum of all of these bits. Because you've got that, I can't remember what it was like this plus that plus that plus that. So that's basically a sum. And you can rewrite this sum as the mass flow rate being the sum of all of these. The sum of all of these. This little equation here, it's saying that the sum of the difference in mass flow rates at each I. I is basically each of the readings you're taking. So for this reading, for example, I1, I2, I3, reading 1, reading 2, reading 3, going all the way up to the number of readings that you've taken. And you're going to sum all the different ones that you've taken, and that will give you the mass flow rate. And we know this here, dm, we can plug that back in here, from there, from above. And then we can take this rho 2 pi outside of the sum, because that's not really related with our r's. Leave all the r's inside there, and we have ended up with the equation for mass flow rate through the pipe using a velocity profile measured using a pitot tube.